Cool. Thank you very much. Welcome, everyone. Thank you for coming. As was just mentioned, I'm going to be talking about Spark Autotuning. I'm going to start out talking a little bit about our motivation. Why did we feel it was necessary to build this technology? I'll then talk a little bit about the technology itself, and then finish up talking about where we anticipate taking this technology next. So motivation. So by way of introduction, I work at Alpine Data. It's an advanced analytics startup headquartered in San Francisco, and we build an enterprise-grade data science platform. It's an end-to-end solution that takes data scientists from problem definition right the way through to model operationalization, where you're pushing sort of PMML and PFA models out to real-time scoring engines across the broader enterprise. And to do that, we make aggressive use of Spark, right? We use Spark at pretty much every step in that process. And there's a variety of different ways of interacting with the Alpine Data Science Platform. Probably the most common is via our visual analytics builder. It's a code-free drag-and-drop visual interface where basically you just sort of drag operators on and create your flow. So for example, if you want to build a flow, you'd browse HDFS, find the data set you want, drag it on to the canvas. Then maybe it's got some missing values, so you drag on a null replacement operator. You connect that up. Maybe you want to normalize some of the columns, so then you drag on a normalization operator, connect that up to the output of the null value replacement operator. And then finally, maybe you want to train a random forest. You grab the random forest operator from the palette on the left, drag that onto the canvas, and then connect that to the output of the normalization operator. And then you click go, you click run. And at that point, the software basically parses the computational DAG that you've built, the flow, synthesizes an execution plan, and then pushes that compute down to the cluster for execution. And so this is a very efficient way to do data science. We've introduced a level of abstraction where the data scientist is focused on the data science problem. They don't have to care about Spark. They don't have to care about the execution framework. It could be Spark, could be Flink, could be what have you. They don't need to care about the cluster, the size, the configuration, the permissioning, the authentication. They're focused on the data science problem. So as I said, we use Spark, and we use it because of the performance benefits. But as you guys know, Spark is extremely sensitive to the resourcing and job configuration. And so if you're not careful, you end up with a situation where you're actually having to ask the data scientist for guidance about how to configure the Spark job, the number of executors, the size of the executors. And now we've shattered that layer of abstraction. Now the data scientist needs to know about Spark, needs to know about the cluster, the configuration, really the nuts and bolts of data science. Of sort of big data, sorry. And this then becomes a very sort of inefficient, laborious trial and error process where you'll see sort of the data scientist hit go. The job will run for some number of minutes, some number of hours before potentially dying with some sort of an error, particularly an out-of-memory error. And then it's sort of you bump the resources a little bit, you try again, and you iterate until you actually get a successful configuration. So it's extremely laborious, it's extremely time-intensive, it's extremely inefficient. And really you end up with a suboptimal solution at the end. Typically you're just sort of excited that your Spark job actually ran to success. But it could well be that you're significantly under-resourcing your job, such that if you gave it additional resources, it could run 2, 4, 5, 10 times faster. Or maybe you're significantly over-resourcing your job, such that you're being sort of wasteful and squandering scarce cluster resources. And so really what you want is basically software that can figure this out for you. Basically software that looks at the analytical flow that's been built by the data scientist, comes up with a resourcing estimate for that flow, and then reconciles that flow against the resources on the cluster you're pushing it down to, all automatically without user involvement. And if you think about it, we're continuing to add additional layers of abstraction between the data scientist and the underlying execution frameworks. So think about AutoML. Here, the data scientist is not interacting with Spark on a per operator basis, but is rather providing to the software a data set, saying this is the outcome I'm interested in, go explore it automatically for me. So the software is basically trying a bunch of different feature engineering techniques, it's trying a bunch of different ML algorithms, it's potentially even looking at hyperparameter optimization, and then returning the best available options to the data scientist. And so at that point, it becomes even trickier to invite the data scientist in to help configure and resource the Spark jobs that are running under the hood. And then if you take it one step forward, if we start to think about sort of intelligent BI, there's maybe not even a data scientist in the loop. you have an analyst who's interacting visually with their data set, and then the software is automatically launching machine learning jobs under the hood to basically surface insights, guidelines, and recommendations. And so you really do need, at that point, the system to be capable of thinking about how to resource and configure those jobs itself. And so, basically that's our motivation. That's why we set out doing this. And we started this process about 9 months ago. We released our initial version of this autotuning logic in the Alpine Data platform in the fall. And since then, we've been sort of iterating and tuning it and refining it on every subsequent software release. So let's talk a little bit about the algorithm itself now. Unfortunately, due to both sort of time and intellectual property considerations, it's not possible to talk about the exact algorithm that Alpine is using in its data science platform. However, what I can talk about is a sort of more example algorithm, which is something we played with in the early days as we actually started down this discovery process, and we found to be surprisingly robust and surprisingly helpful. So let's dive into that. Before we do that, let's start off with what is exactly we are trying to configure and resource. So here we have the sort of obligatory Spark architecture diagram. We have on the left the Spark driver. It could be running on the client or on the cluster, and we need to size that. How many cores, how much memory. We have one or more executors running on the cluster. We need to size that cores and memory. We then also need to figure out how many executors we want to throw at the problem. And then finally, we need to think about how we want to partition our data such that we can actually make effective use of the executors that we're spinning up. And so what does this depend on, right? What are all these parameters influenced and, basically depending on? And there's a wide variety of different things that you need to take into consideration. Firstly, obviously, the size of the data. The more data you have, probably the more compute you want to throw at the problem. But it's also influenced by the complexity of the data, the dimensionality of the data, the cardinality of the data can actually have a big impact on sort of some of the algorithmic requirements of the different operators. The complexity of the algorithms itself, it depends, there's a big variation between having a sort of simple single-pass ETL flow versus a compute-intensive machine learning algorithm. Also, the nuances of the implementation itself. How well was the algorithm actually written? Was the developer wasteful with memory? Were they wasteful with compute resources? That's obviously going to dictate how much is used as well. And so that's on the algorithmic side. And then we need to sort of map those resource requirements down to the underlying hardware. So obviously, it depends on the cluster size, the number of nodes, the memory per node, the cores per node. It also depends how we've configured our cluster as well, the yarn configuration, the Spark configuration. And then finally, unless you're one of those people who's actually lucky enough to have a sort of dedicated Hadoop cluster sitting under your desk, it's typically a shared resource, right? So you basically don't have permission to use the entire cluster. There's other people using it simultaneously, and so you need to figure out what the available resourcing is on that cluster at the point that you actually want to submit your Spark job. And so a couple of questions that may initially come to mind is, why can't I just use the default settings? Aren't they good enough? Well, the answer is absolutely not. These are just settings to get you going, right? They're for toy data sets, small clusters. They're not really applicable to doing real-world data science. Second question is, if you troll the web and look in Stack Overflow and stuff, you'll see various resourcing calculations out there. Can you use those? Well, a lot of those are fairly simple, and they assume a dedicated cluster and assume that you want to use all of the resources associated with that cluster. Now, that's fine if it's a dedicated cluster and you're the only person running and this is the only job you want to run, but it's extremely wasteful and certainly not applicable to a more typical enterprise scenario where there's other people competing for resources and you don't want to squander them unnecessarily. So before we jump into the actual algorithmic details, one thing to keep in mind, there's a bunch of equations on subsequent slides in this presentation. And for clarity purposes, I've removed a lot of the sort of overheads and modifiers that you need to take into account, rather talking about things like available memory or usable memory. But if you actually sort of do this exercise yourself, you need to remember there are all of these overheads around, so the actual available memory to your Spark executor doesn't necessarily map to the yarn container size and things like this. You need to factor in all of these as you're doing these resource configurations. But as I said, I've sort of removed them on the subsequent slides for clarity purposes. So basically, what are we attempting to do? As we said, that basically, if you think about the visual UI we have, a flow is being constructed by a user. We need to understand the resources associated with that flow. We need to reconcile that with the available hardware resources. And the answer may be, well, why can't we just set everything to the maximum, right? And really, it comes down to the fact that we have a finite amount of resources on that cluster, and that actually introduces interdependencies between all of these different Spark configuration values. I mean, if you think about it, for example, if you increase the executor memory, it probably means that you need to decrease the number of executors, right? You have a finite amount of memory to throw at the problem. Similarly, if you increase the number of cores per executor, the amount of memory available per core will actually decrease because there's obviously going to be an upper bound on the maximum size of executor you can field that's actually set by the yarn container size. And so there's all of this interdependency, and if you set one value, it typically ripples through and causes modifications of the others. So it sounds like a tricky problem to solve for. The one thing that we do have on our side is there's not just one correct answer. Then maybe it could be argued one peak performance configuration that will give you the absolute peak performance. But around that configuration are a number of other configurations that will deliver sort of reasonably good performance. And so our job is really looking at those configurations and finding one that actually maps well to the available resources on the cluster that we have at our disposal. And basically, that's a much easier problem to solve for, and that's basically what the algorithm is attempting to achieve. So the first thing we want to do is actually understand the algorithmic requirements themselves. And so we can start doing this by looking at the size of the input data, looking at the complexity of the input data. So if you remember back to that flow that the user built, it has an input data set. We're interested in the size of the input data set for two reasons. First, obviously, the bigger the data set, the more computationally intensive it is to actually go and analyze that. The other thing, if you think about it, is a lot of the performance benefit from Spark is because it caches relevant data in memory as RDDs. It's not spilling to disk and reloading constantly. So we actually want to start to try and estimate what the size of the RDD is going to be associated with this input data set. And so basically, when the user clicks run, we actually run out and we sample from the input data set. And we use that sample to actually estimate the schema. We do schema inference. We look at the dimensionality of the data. We look at the cardinality of the data, and we also estimate the row count of the data. And using that information, we can actually estimate the size of the RDD that's actually going to be created by that input data set. It's not always necessary to do this at runtime. If you're doing it at runtime, you want to sort of do a very lightweight analysis, but you can imagine a scenario whereby when a user creates a new data set or uploads a new data set to the cluster, sometime when the cluster is idle, a background process gets kicked off to analyze the data in much more detail, and then basically a thumbnail sketch of the data is stored in a metastore for retrieval at runtime. So you have a much more comprehensive understanding of the data set, and you can use it to really understand sort of the algorithmic nuances of downstream algorithms. The other thing to take into consideration is what we've done here is we've just looked at the size of the input data set. It's obviously modified as it flows through that computational DAG. And so we need to understand the impact of downstream operators and on the state being sort of transferred from operator to operator. And we have three examples here. Here on the topmost, we're loading from a CSV. We're doing null value replacement, normalization, logistic regression. And so basically, the state being passed from operator to operator is pretty much the same. The columns being passed remain the same. In the next example, we're actually doing sort of a dimensionality reduction using PCA. And so downstream of this operator, the amount of state that's being pushed forward is reduced significantly. We have the other end of the spectrum here, where we're doing something like one-hot encoding, and the number of columns and state that's being moved forwards down this computational DAG is basically increased significantly. And so it's not only thinking about what is the initial input data set, but also how that morphs as it flows down this sort of computational DAG. So we can use that to get a sense of the RDD sizing, the basically raw size of the data set, and then we can also start to consider the algorithmic complexity. There's a variety of ways to do this. The way we're going to talk about today is actually surprisingly simple, but we found to be fairly effective in the initial version of this algorithm. Because this is a hard problem to solve for, right? I mean, these basically span the entire spectrum of sort of, memory requirements, core requirements, compute requirements. And so what we did in this instance was, given that we have sort of a toolbox that's available to us of different operators, is compute for all of the operators basically relative complexity modifiers, such that on an algorithmic basis, we can say this guy uses a lot of compute, this guy uses a lot of executor memory, this guy uses a lot of driver memory. And then when you basically walk the DAG that's being constructed, you can understand the various computational and sort of resourcing requirements of the different operators in this flow. It's actually a very simple scheme, works surprisingly well. As you guys can imagine, there's a bunch of much more sophisticated ways of actually inferring this computational complexity. We can also extend it as well, so it's not just the operators in the toolkit. We actually wrap a lot of open source algorithms as well, things like MLlib or H2O. And you can do the same there. When you wrap the algorithm, provide relative modifiers to indicate to the auto-tuning algorithm the relative requirements of the algorithm that you're focused on. And then also, if you're writing your own code that you want to make into an operator and provide for other users in your group, you can provide the same tuning information to the auto-tuning algorithm. So that's basically looking at the resource requirements of the flow as it stands. The next thing to think about is how this actually maps down to the real-world hardware. So the first thing we need to think about is we talked about the fact that this is a shared resource. We're only going to get some part of it. And so that resource management is typically done using yarn queues, right? And so we need to figure out what queue we're going to map to and what is the resourcing associated with that queue. It can be mapped on a per user basis, on a per group basis, or also just everyone using a single app is mapping onto the same queue. And so we need to figure out basically what are the resources we're entitled to in the queue, who else is mapping to the queue, how much of the queue is currently being utilized. And there's basically a billion different yarn configuration parameters associated with this, governing the elasticity of the queue, the maximum percentage of the queue a single user or a single app or job can leverage, and we need to pull all that information back. In addition, on a per queue basis, you can actually set the maximum yarn container size, which obviously governs the maximum size of the executors we can leverage, so we also need to pull back that information as well. The other thing we need to understand on the queue is obviously on the cluster, is whether dynamic allocation is enabled, right? So this is the ability of Spark to dynamically add additional executors if for a certain period of time there are pending tasks and there are available cluster resources. This can make it much easier to determine obviously the upper limit of the number of executors you want to throw the problem. It is a little bit more tricky in an enterprise environment where you want to understand the queue resourcing and make sure that you don't make yourself unpopular with the remainder of the sort of people using the queue by overcommitting the cluster. And then even if you are leveraging sort of dynamic allocation, you still need to understand the basically shape and size of the base executors themselves. So how many cores, how much memory. Luckily, we can pull all this information from the Yarn Resource Manager. It exposes a very rich REST API that allows us to basically go and pull in all of the information we need about the queue types, the queue resourcing. In addition to that, we can also pull information about the real-time utilization of the cluster. And this is not just the sort of aggregate utilization across the cluster, but we can do this on a per node basis and figure out the available resources across every active node in the cluster. So once we have this information, let's start actually using it. And so one of the things we can do first is basically in this simple algorithm, let's just set a value, figure out what that means for the rest of the parameters, and then iterate as necessary. So there's a variety of different ways you can start out. One of the ways that we found works well for this sort of simple algorithm is basically say, let's try and consume resources in relation to their relative abundance. And that makes sense, right? In essence, you don't want to use all of the memory for a single executor, and then you're computationally constrained. Nor do you want to throw a lot of executor cores at the problem and find that you're basically starved all of your executor cores. You've overwhelmed them because they have insufficient memory to actually do anything useful. And so let's start with a balanced strategy. So one thing we can do there is basically look at the amount of memory we have available in the queue, look at the amount of cores we have in the queue, and that gives us an estimate for how much memory we can spend per core if we want to consume them in a balanced way. We can also start to introduce some of these relative complexity modifiers. So as we walk the DAG that are being constructed, if we see algorithms there that are particularly memory hungry, use a lot of executor memory, then we can bump up this ratio to accommodate that. Once we have that number, we can then start to think about how many cores can we support per executor. And so here what we can do is look at the maximum memory that we can have in a yarn container, obviously subtracting out all those overheads we talked about at the start, divide by the memory per core, and that gives us an estimate for the number of cores that we want to actually associate with an executor. We probably want to limit that. If you go out and look on the web, there's a bunch of sort of tribal wisdom saying that the efficiency with which Spark uses executor cores starts to diminish after some point, and some people are even setting this as low as basically 5 cores. Once we have that value, we can actually compute the memory of the executor itself. We can take the memory per core, multiply it by the cores per executor, and that's basically sizing our executor for us. Once we have that determination, now we can start to look at how many executors can we actually support on the cluster at present. And so we can use the real-time resourcing information that we pulled from the Yarn Resource Manager, and on a per-node basis, look to see how many executors we can support. And so there's going to be a constraint introduced by the amount of memory, a constraint introduced by the number of cores. We take the minimum of those two, accumulate over the active nodes in the cluster, and that gives us the available number of executors. That's basically the maximum that we can field at present without overloading the cluster. We can then also consider the queue constraints, basically how many executors can we do without violating the queue memory constraints, how many can we do without violating the queue core constraints, and then take the minimum of all of these three. And this basically gives us an upper bound on what we can field and what we can use. So it's the upper bound of usable executors. How many actually do we want to use, though, right? We don't necessarily just want to leverage all of them straight out of the box. So what we can do here is basically leverage the sort of RDD size or cache size that we computed earlier on, and then basically divide that by the amount of memory that each executor has dedicated to sort of RDD storage. And this gives us the number of needed executors basically to keep the sort of relevant data in memory without spilling. So then we can use that value to basically figure out the final executor count. So we need to keep in mind what's actually feasible given the available resources on the cluster. And then we can take this sort of memory-based number and actually modify it if we see a lot of compute-hungry algorithms in the flow that we've basically just built. From a data partitioning standpoint, we want to make sure that we have enough data partitions to keep all of the executors that we're throwing at the problem busy. So the simplest lower bound on this, in essence, is the number of executors multiplied by the cores per executors gives us the minimum number of partitions. We also want to make sure that we're basically not overwhelming each of the executors. So we can do a calculation here where basically we're looking at the Spark execution memory and making sure that we're not overwhelming it when we look at the size of the RDD, right? So basically we take the size of the RDD, divide it by basically the memory we have available for execution purposes, and that also gives us a good estimate for the number of partitions that we actually want to set to avoid overwhelming the executors. And then we can take the maximum of those two values, and that gives us the final partition count. Driver sizing. In the simplest implementation of this, we basically said, hey, the driver looks like another executor. We use some of these modifiers to say, if we see a lot of algorithms that are going to make a lot of use of driver memory, then we want to boost this accordingly. Obviously, we then need to take into account the fact that we're spinning up an additional resource, and so reduce the executor count if needed, if we're bumping up against the limits imposed by the queue or the available resources on the cluster. And then finally, sanity checks, right? I mean, this is a fairly generic, broad algorithm. There's always going to be edge cases, and so you want to make sure the algorithm doesn't do anything too crazy. So make sure that you're not spinning up some crazy partition counts, that the resourcing for small files is not over the top. I think in the initial version of this, we actually had a special path for small files, such they didn't even go through this logic, but said, oh, look, let's just throw a couple of executors at these rather than trying to push it through the normal logic. And also as well, make sure that we're not trying to squeeze a massive job onto an overwhelmed cluster as well, right? So basically, we are trying to adapt the needed resources to the available resources, but we don't want to push that too far and just overwhelm the cluster or have a job that basically is making no forward progress. So it's all about the edge cases. And then also iterate if necessary, right? You can go through this process multiple times, set an initial value up front, see what that flows through for all the different values, see whether they make sense, and then do another pass by modifying some of those. So just finally to talk then about future improvements. A couple of things obviously jump out. Once you understand the resourcing associated with a flow, you can not only use it for configuring the job itself, you can start to use it for sizing elastic environments such as cloud EMR, right? So we've done a lot of work looking at sort of AWS EMR environments, and rather than keeping your entire Hadoop cluster hot the entire time, you can have a base set of nodes and then have the software automatically, dynamically add compute nodes and remove compute nodes as needed. And this can then lead to significant sort of cost savings and significant performance benefits. The other thing you can think about doing as well is that most flows will be run multiple times. They may be part of a scheduled job, there may be multiple users running them, maybe even the same user is running them repeatedly to basically try different configuration settings. And so basically we can record the settings that we chose, and during the runtime of the Spark job, we can basically query the Spark APIs to understand how the job is faring on the cluster. We can record all that state and hence improve that, use that to guide us in the subsequent iteration of the job being run. So to conclude, clusters are noisy. It's a difficult problem to resource Spark jobs correctly. It's made even more difficult by these noisy enterprise clusters. You can spend a lot of time sort of manually trial and error iterating through this. What we need is software that does this automatically. Happily, it is possible to create this software, and what I've hopefully illustrated today is that even simple estimators can do a pretty good job, right? Are they going to fix all problems? No, but they can fix the lion's share of the problems that data scientists are wrestling with today, even using a very simple algorithm such as we have here. So I've glossed over a lot of this, right? There's a lot of corner cases, a lot of our sort of thinking and logic, and we didn't even have time for any examples just because of the time constraints we have. So I will follow this up with a blog on our company website that will talk more about the details, provide some examples about how the logic works, and actually provide some Scala code fragments that people can use. One final acknowledgement, Rachel Warren was the lead developer on this project in my team. She would have been here today helping, but she is trekking through South America at present. So thank you. Come by the booth. I think you've maybe got 10 minutes before it closes. So let us know if you have any questions. Thank you. Certainly, I mean, essentially what we have here as well is that the Alpine Data Science platform is a collaborative environment, and we often have up to installs at some of the bigger financial firms. We have about 100 analysts concurrently using the platform. And so we do not only on a single basis, on a single flow basis, but we actually have additional logic on top of that that's looking across the entire resource burn of all of the users using Alpine, and that's being used to size sort of AWS clusters and things like that.
Hi, thank you very much. It was a very informative talk.
Thank you.
I was wondering, one of the first slides you mentioned that there was implementation nuances that have to be considered in order to tune this. And I completely agree. There are these situations where it's not about the memory, it's the fact that the data is skewed, or the approach that you're using, you're not filtering soon enough, things like that, right? So how is that? Could you please elaborate a little bit more in those kind of improvements? Are they happening automatically? How can you do that?
So I think it's twofold. I mean, I think firstly, you know, as we do a more sophisticated analysis of the data set, we can pull more sort of statistical information about how the data is, you know, skews in the data, sort of the cardinality of the data, and that can be provided to sort of the algorithms, such that the algorithms, you know, we can get feedback from the algorithms basically around their resourcing requirements. That said, at the end of the day, if the algorithm is just unsuited, or if you're basically going to need sort of almost like infinite resources based on the data because of the algorithmic choices chosen by the developer, there's not so much we can do there, right? I think the best thing we can do at that point in time is actually provide more informative error messages, right? Actually explain to them why it's failing, at what stage, and what the problem is, right? Because some of the Spark out-of-memory errors can be fairly difficult to diagnose, right? And then you really have to drill in and figure out what's going on. So I think we can make that much easier. So there's only so much we can do if the algorithm is just unsuited to the data that's being thrown at it, or it wasn't built to scale that far, or just not built with big data. But we can make this sort of approach to people debugging that much simpler.